let's take a look at this one. Calculator. Just so we can kind of visually see this thing as well. We should see a function that is approaching 5 at 0. So we're going to go back and put in the original problem I gave you guys to work on here into your y equals. So that should be in parentheses 2x plus 3 sine x all divided by x. So something kind of like that. Double check that your mode is in radians. Mine's not. Oops. Should be in radians. And your window, maybe let's go to like 8 in every direction. We know the limit's equal to 5, so we want to make sure 5 is in there so we can see it. All right, so if we graph this thing, when x is 0, the function should be approaching 5. All right, so does it appear as though the function is at 5 when x is 0? Yep. Is the function actually equal to 5 when x is 0? Look at the original equation we used. Can I plug in a 0? So does the function have a value at 0? No. If I can't plug the number in the original equation, then the function itself does not have a value there. Now, why the heck did the calculator graph it like this then? Because the calculator works in teeny tiny little pixels. Okay? There's actually a hole right here that you can't see. Right at the top of that hill. It's got a removable discontinuity right at the top of the hill. Okay? So as you approach 0 from either side, you're approaching the value of 5. But if you try to actually plug in a number there, if you actually try to plug in a 0, I can even do that. Calculate value x equals 0, and my calculator is even going to tell me nothing there. X equals 0, y equals nothingness, which means undefined. Okay? So there's nothing there, but the limit does exist because from either side it is approaching that value of 5. Okay? So we have verified that graphically now. That, yeah, that's right. That limit should be 5. Okay. Last thing I want to talk about today is something called the sandwich theorem, and this would be kind of your fourth thing that you want to check here for with limits. All right, and so the sandwich theorem says this. Let's say I've got some function f of x heading along there, and I want to know what's the limit of that function at c, right there. So what's that limit right at that spot? And let's say for whatever reason I cannot calculate it by hand. But I am aware of this other function, g of x, that is always above this function up here. And I'm aware of this other function, call it h of x, I guess, that is always below f of x. Like that. So, if g of x is always greater than f of x, and h of x is always less than f of x, and the limit as x approaches c of g of x and h of x is the same thing, then f of x has to be that as well. Because g of x and h of x have sandwiched that value at that spot. Does that make sense? This one always has to be on top, this one always has to be on the bottom. And at this particular value, if those two are the same, then f of x has to be the same too, because it has to be in between those. So it has to be that exact same thing as well. It is very rare that you run into a situation where this is actually going to work out. Now, there are some specific ones we're going to look at. And you'll kind of, after a while, know them when you see them. Like, oh, that's a sandwich theorem one. Or the directions will simply state, use the sandwich theorem to determine this limit. Okay? So that's kind of the visual of what's going on. As far as what it says, specifically, if g of x is greater than or equal to f of x and h of x is less than or equal to f of x, for all x not equal to c, then if the limit as x approaches c of g of x equals the limit as x approaches c of h of x, and that's equal to some value, we'll call it L, then the limit as x approaches c of f of x also equals L. Okay, so let's use it once. Show you how it works. Whoopsie. Alright. This will be where we finish up today. So let's find the limit as x approaches 0 of x squared sine of 1 over x. Okay, so we're looking at one where, like the other methods won't work, right? If you try and do a substitution, can't do it because you can't divide by 0 again, right? Because it's the sine of 1 over x. If you try to do, what was the next one? Simplifying, you can't simplify x squared sine 1 over x. There's nothing to simplify. Properties aren't going to help you. There's no properties that we can use to break this up at all that are going to allow us to do it. So we're on to our sandwich theorem line of defense here now. So first thing we need to do is, if this is our f of x, we need to come up with two functions, one of which that's always above this and one of which that's always below this. And that seems like a pretty tall order. Like, how in the world am I'm just going to randomly pick two functions that work, that one's always bigger, one's always smaller? Well, yes and no. The fact that there's a sign in this thing helps get started. Sine of 1 over x. We're going to ignore the x squared for right now, okay? But any trig function, as long as you're not multiplying it by something, every single trig function, sine and cosine, are caught between two numbers. Now think y values now, right? What y values are sine and cosine always in between? If there's no change in amplitude, just a regular old sine wave. -1 and 1, right? So I've already got this much of it sandwiched. So your sandwich theorem problems are almost always going to have a sine or a cosine in them because you can start it like this. Now, some of you guys might be a little confused, really. Well, hold up. What about this 1 over x? How does that not change what these are on the outside? Nope, it doesn't. Because whatever you do to the inside of this function here only affects it horizontally. Doesn't affect it vertically. You guys remember that from transformational stuff? Anything done to the inside of a function affects it horizontally. Okay, moving it left and right, stretch and shrinking left and right, whatever. Doesn't affect the fact that it's between -1 and 1. That's still a true statement, and I can still start that way. Okay? So, knowing this fact then allows me to go one step further with it and say, okay, if that top statement is true, what if I take that middle and multiply it by x squared? Okay, well, think about like an equation. Whatever you do to one side of an equation, you got to do to the other. I've got a compound inequality happening here. I've got two inequality signs. Well, whatever I do to the middle of that, I have to do to the other two pieces as well. So if I'm going to multiply the middle by x squared, I got to multiply -1 and +1 by x squared as well. So now I've got my two functions that are trapped, or that it's trapped in between, -x squared and x squared. And I am hoping that if I take the limit of these two guys as x approaches 0, I get the same answer. Because if I do, whatever that answer is, it's the same for the one in the middle then. Okay? That's how that sandwich theorem is going to work. So let's check that then. So the limit as x approaches 0 of -x squared. Can I do that limit? Remember, what's the first thing you always try? Can I plug in a 0? Be careful. Of course you can. Yeah, it's just 0, right? -0 squared? 0. And limit as x goes to 0 of the other side, x squared? Also 0. So the function that's always above it comes out to 0. The function that's always below it comes out to 0. So based on that fact, both of these two limits equaled, in this case, 0. So therefore, the limit as x goes to 0 of f of x should equal what? 0 as well. Yep, it's got to be the same thing. So this would be limit as x approaches 0 of x squared sine 1 over x equals 0. Okay, so let's real quick graph and take a look at that. Double check, make sure we're right, and then we'll be done. So back to our calculator here. So our function was x squared sine of 1 over x. And we're looking to see at 0, what is it approaching? Remember, it's not going to have a value there, right? If I try to put 0 right there, it doesn't work. But we're looking for the limit as x approaches 0. And it does appear to be doing that. Okay. And in fact, this function gets a lot more interesting if you make the window smaller. So, actually, is that right? Radiant, yeah, okay. Let's see if I make this, let's just do this real quick. We're gonna have to make that even smaller. It's supposed to look all wavy, like I think it has to be like super small. Yeah, so it's kind of doing a little bit there when you get really, really small. And you guys can kind of see that, right? Where that limit is. Okay, it's like coming kind of wavy-like in this way, wavy-like in that way. But it is approaching 0 from either side. Okay. Busy people. Okay. So I'm going to stop there. And then remember, tomorrow is your first online day, so you should have a self-assessment. There's a little website where you guys can practice with doing some limits, and they'll let you know if you get them right or wrong. And then there's a homework assignment, and then don't forget about the attendance.